There are several factors to consider when evaluating if a building's electrical service is adequately sized. Firstly, consider the building's actual load. The customer's estimate of 6 watts per square foot may be too high for the average tenant requirements in their building. This could be influenced by several elements. These elements are firstly, the type of tenants occupying the space, secondly, the age of the building itself, and thirdly, the efficiency of the building's various systems. Secondly, the building's diversity factor should be assessed. The diversity factor quantifies how evenly the electrical load is distributed across the building's tenants. A higher diversity factor implies a more uniform distribution of load, which in turn can reduce the peak demand placed on the service. Thirdly, the building's demand factor needs evaluation. The demand factor measures the proportion of the building's total potential load that is actually utilized at any given time. A lower demand factor suggests that the building's load is not characterized by significant peaks, which can also contribute to reducing the peak demand on the electrical service. Fourthly, one must account for the building's power factor. A power factor reflects how efficiently the building's electrical system utilizes power. A lower power factor can lead to an increase in the peak demand on the service. In addition to these factors, it's important not to overlook the following elements. Firstly, consider the building's future load. The building's electrical load may increase over time due to factors such as tenant growth or the introduction of new electrical equipment. Secondly, consider the building's redundancy requirements. The building might necessitate redundant electrical systems to ensure continuous operation, even in the event of a power outage. Thirdly, maintenance requirements should be considered. The building's electrical system will require regular maintenance to ensure its proper functioning and longevity. To delve into the details of demand factors, let's explore the concept thoroughly. The demand factor is the ratio of the maximum demand of a system, or part of a system, to the total connected load of the system or the part of the system under consideration. This factor is always less than 1.0 because the maximum demand can never exceed the total connected load. The formula for calculating demand factor is demand factor equals maximum demand divided by total connected load. For example, if a building has a total connected load of 1000 kilowatts and its maximum demand is 750 kilowatts, the demand factor would be 750 kilowatts divided by 1000 kilowatts, which equals 0.75. Demand factors are used to estimate the size of electrical services required for buildings and other electrical systems. They allow engineers to design systems that are adequately sized for the anticipated load without being excessively large and costly. Demand factors vary depending on the type of building, the types of tenants, and the climate. For example, a hospital will typically have a higher demand factor than an office building because hospitals have more critical loads that must be served at all times. Similarly, a building located in a hot climate will have a higher demand factor during the summer months due to the increased use of air conditioning. Electrical codes, such as the National Electrical Code, provide guidance on the demand factors that should be used for different types of buildings and occupancies. These codes are based on historical data and industry best practices. It's important to consult the applicable electrical codes when designing electrical systems to ensure that they are safe and reliable. Now let's elaborate on diversity factor. The diversity factor is the ratio of the sum of the individual maximum demands of the various subdivisions of a system to the maximum demand of the entire system. It reflects the likelihood that not all individual loads within a system will operate at their maximum demand simultaneously. The diversity factor is always greater than or equal to 1.0, as the maximum demand of the entire system cannot exceed the sum of the individual maximum demands of its components. The formula for calculating diversity factor is diversity factor equals sum of individual maximum demands divided by maximum demand of the entire system. For example, consider a building with multiple tenants. If tenant A has a maximum demand of 100 kilowatts, tenant B has a maximum demand of 150 kilowatts, and tenant C has a maximum demand of 200 kilowatts. The sum of the individual maximum demands is 450 kilowatts. If the maximum demand of the entire building is 350 kilowatts, the diversity factor would be 450 kilowatts divided by 350 kilowatts, which equals approximately 1.29. Diversity factors are used in electrical system design to account for the fact that the total load on a system is not simply the sum of the individual loads. By applying diversity factors, engineers can more accurately estimate the peak demand on a system and design the system accordingly. Diversity factors vary depending on the type of system, the type of loads served, and the operating characteristics of the loads. For example, a residential electrical system will typically have a higher diversity factor than an industrial electrical system because residential loads are more diverse and less likely to operate simultaneously. Electrical codes and standards provide guidance on the diversity factors that should be used for different types of systems and loads. Consulting these resources is essential when designing electrical systems to ensure that they are safe, reliable, and cost-effective. Power factor is another important factor to consider. Power factor is the ratio of real power, measured in kilowatts, to apparent power, measured in kilovolt amps. It represents how effectively electrical power is being used. A power factor of 1.0 or 100% indicates that all the power supplied is being used to perform useful work. A power factor less than 1.0 indicates the sum of the power is being wasted due to reactive loads such as inductive loads from motors and transformers. The formula for calculating power factor is power factor equals real power, kilowatts, divided by apparent power, kilovolt amps. For example, if a facility has a real power demand of 800 kilowatts and an apparent power of 1000 kilovolt amps, the power factor would be 800 kilowatts divided by 1000 kilovolt amps, which equals 0.8. A low power factor can lead to several problems, including increased energy costs, reduced system capacity, and voltage drops. Utility companies often charge penalties for low power factors, as they must supply the additional reactive power required by the load. To improve power factor correction capacitors can be installed to offset the effects of inductive loads. These capacitors supply reactive power to the system, reducing the amount of reactive power that must be supplied by the utility. Power factor correction can result in significant cost savings and improved system performance. Electrical codes and standards provide guidance on power factor correction and the levels that should be maintained. Power factor should be considered when evaluating a building's electrical service. Now let's delve into the National Electrical Code, or NEC, and its relevance to the topic. The National Electrical Code, or NEC, is a widely adopted standard for the safe installation of electrical wiring and equipment in the United States. It is published by the National Fire Protection Association, or NFPA, and is updated every 3 years. While the NEC is not a law itself, it is often adopted by state and local jurisdictions as part of their building codes. The NEC provides detailed requirements for all aspects of electrical installations, from wiring methods to overcurrent protection to grounding and bonding. It covers a wide range of occupancies, including residential, commercial, and industrial buildings. Several articles in the NEC are particularly relevant to the topic of building electrical service sizing. Article 220 covers branch circuit, feeder, and service calculations. This article provides detailed methods for calculating the loads that will be served by an electrical system, including general lighting, receptacle outlets, and specific appliances. Article 230 covers services. This article provides requirements for the service entrance conductors, overcurrent protection, and grounding of electrical services. Article 310.15 covers ampacity of conductors. This article provides tables and guidelines for determining the allowable ampacity of conductors based on the size, installation type, and installation conditions. These are just a few examples of the NEC articles that are relevant to building electrical service sizing. It is important to consult the NEC and other applicable standards when designing and installing electrical systems to ensure that they are safe and compliant. The NEC provides specific requirements for calculating the minimum size of service entrance conductors based on the calculated load. These requirements take into account the demand factors and diversity factors that are applicable to the specific type of occupancy. The NEC also provides requirements for overcurrent protection of service entrance conductors to protect against overloads and short circuits. Proper grounding and bonding of the electrical system is also essential for safety and is covered extensively in the NEC. In addition to the NEC, other standards and guidelines may be relevant to building electrical service sizing, such as those published by the Institute of Electrical and Electronics Engineers, or IEE, and the American National Standards Institute, or ANSI. These standards provide more detailed guidance on specific aspects of electrical system design and installation. The local utility company may also have requirements for the connection of electrical services to their grid. These requirements may include specific metering requirements, protection requirements, and power quality requirements. Working closely with the utility company is essential to ensure that the electrical service is properly sized and connected. Moreover, it is crucial to consider the building's future needs when sizing the electrical service. It is often more cost-effective to install a slightly larger service than is currently needed to allow for future expansion or changes in occupancy. Failure to adequately size the electrical service can result in costly upgrades or modifications later on. Regular maintenance and inspection of the electrical system are also important to ensure its continued safe and reliable operation. Over time, components can degrade or fail, leading to potential hazards. A qualified electrical contractor should be engaged to perform regular inspections and maintenance. Considering future load requirements is crucial for long-term electrical system planning. Overlooking potential increases in demand can lead to premature system obsolescence and costly upgrades. To accurately project future loads, consider factors such as anticipated tenant growth, changes in building usage, and the adoption of new technologies. Incorporating these projections into the initial service sizing can prevent future disruptions and ensure the electrical system remains adequate for the building's evolving needs. Tenant growth. If expansion of the building is planned, it's a factor. Changes in building usage, such as converting office space to a data center, will substantially increase electrical demand. The adoption of new technologies such as electric vehicle charging stations or energy storage systems. The NEC provides guidelines for calculating future loads. Article 220.87, for example, permits using actual historical load data with adjustments for any known changes in the load to determine the existing load. Article 220.3 allows for increasing the calculated load to account for future expansion. In addition to the NEC requirements, local building codes or utility regulations may also dictate specific requirements for future load considerations. Consulting with a qualified electrical engineer is recommended to accurately assess future load requirements and design a service that can accommodate them. Incorporating future load considerations into the initial design not only prevents future problems but can also result in long-term cost savings. By installing a service that is adequately sized for future needs, you can avoid the expense of upgrading the system later. Furthermore, a well-designed electrical system that can handle future loads can enhance the building's marketability and value. Considering redundancy requirements is crucial for ensuring a reliable power supply to critical loads. Redundancy refers to the duplication of critical components or systems to provide backup in case of failure. For buildings with essential services such as hospitals, data centers, or emergency response facilities, redundancy is paramount. The NEC addresses redundancy requirements in various sections depending on the specific application. Article 700 covers emergency systems, which are intended to automatically supply illumination and power to essential loads when the normal power supply fails. Article 701 covers legally required standby systems, which are intended to supply power to loads that are essential for safety or health, but are not classified as emergency systems. Article 702 covers optional standby systems, which are intended to supply power to loads that are not essential for safety or health, but whose interruption could cause significant disruption or economic loss. Redundancy can be achieved through various means, including multiple service entrances, backup generators, uninterruptible power supplies, or UPS, and redundant distribution pathways. The specific redundancy requirements for a building will depend on the nature of its operations, the criticality of its loads, and the applicable codes and standards. For example, a hospital may require multiple service entrances, backup generators capable of supplying the entire facility load, and UPS systems for critical equipment such as life support systems and surgical equipment. A data center may require redundant power supplies, redundant cooling systems, and backup generators to ensure continuous operation. The design of redundant systems should consider factors such as the reliability of the components, the speed of transfer between power sources, and the ability to test and maintain the systems. Regular testing and maintenance are essential to ensure that redundant systems will function as intended when needed. Furthermore, redundancy can improve the overall resilience of the electrical system, making it less susceptible to disruptions caused by faults, equipment failures, or external events. Incorporating redundancy into the initial design is typically more cost-effective than retrofitting it later. Additionally, a well-designed redundant system can enhance the building's reputation and attract tenants who value reliability and uptime. Therefore, it is important to carefully assess the building's redundancy requirements and design the electrical system accordingly. Discussing the building's maintenance requirements is essential for ensuring long-term reliability and safety. Regular maintenance is crucial for preventing equipment failures, extending the lifespan of electrical components, and maintaining a safe operating environment. The NEC requires that electrical equipment be installed and maintained in accordance with manufacturer's instructions and industry best practices. Regular inspections should be performed by qualified personnel to identify potential problems before they lead to failures. The frequency of inspections will depend on the type of equipment, the operating environment, and the criticality of the load. Common maintenance tasks include tightening connections, cleaning equipment, lubricating moving parts, and testing protective devices. Thermographic surveys can be used to identify hot spots in electrical equipment, which may indicate loose connections, overloaded circuits, or failing components. Power quality monitoring can be used to detect voltage sags, swells, and harmonics, which can damage sensitive equipment. Protective devices, such as circuit breakers and fuses, should be tested regularly to ensure that they will operate properly in the event of an overcurrent or short circuit. Grounding systems should be inspected to ensure that they are intact and providing a low impedance path to ground. Batteries in UPS systems and emergency lighting systems should be tested and replaced as needed. Maintenance records should be maintained to track the history of inspections, tests, and repairs. These records can be used to identify trends, predict future failures, and improve maintenance practices. A well-designed maintenance program should include both preventative maintenance tasks, which are performed on a regular schedule to prevent failures, and corrective maintenance tasks, which are performed to repair equipment that has already failed. Preventative maintenance is typically more cost-effective than corrective maintenance, as it can prevent costly downtime and equipment damage. Furthermore, proactive maintenance approach can improve the overall safety of the electrical system by identifying and correcting potential hazards before they cause accidents. Investing in a comprehensive maintenance program is essential for protecting the building's electrical infrastructure, ensuring reliable power supply, and minimizing downtime. It is recommended to engage a qualified electrical contractor to develop and implement a maintenance program that is tailored to the specific needs of the building. The information provided aims to assist in evaluating whether a building's electrical service is appropriately sized. By carefully considering factors such as the actual load, diversity factor, demand factor, power factor, future load, redundancy requirements, and maintenance requirements, you can make informed decisions about the adequacy of the electrical service. Consulting with qualified electrical engineers and contractors is essential to ensure that the electrical system is safe, reliable, and compliant with applicable codes and standards. If the customer's calculations are based solely on a per square foot estimate without accounting for these variables, the assessment is likely inaccurate. A comprehensive load calculation performed by a qualified professional is necessary to determine the actual electrical demand of the building. Remember to consider that the information presented should not be considered exhaustive, and additional factors may be relevant depending on the specific circumstances of the building.